If we provide 0.818 multiply with this number 8.889, that is gain 7.27. Exactly the calculated output is here. Operational amplifier. It is a linear IC, receives two input signals, compares the signal level at both input pins, determines the difference, and amplifies that signal with our predefined ratio, that is called gain. We will discuss all parameters of operational amplifier. We will perform calculations. We will calculate its necessary components. We will apply power, and we will correlate our calculation with practical test results. Let's start. Assalamu alaikum wa rahmatullahi wa barakatuh. I am your host Muhammad Ashraf, and I welcome you on my YouTube channel. If you are new to my channel, you can subscribe it. If you want to watch videos in future, you can press bell icon button so that you will be notified for my future uploads. For reference, I am using LA6358. It is from Sanyo. If we discuss from the other manufacturers, LM358 8-pin IC. Cut here, pin 1, 2, 3, 4, 5, 6, 7, 8. If you see its symbol, output, 2 inputs, power supply pins. It is 2-channel operational amplifiers. That means there are 2 operational amplifiers within this IC. I will not go in very detailed theories, what is inside, how many transistors are inside. That is difficult to understand. Pin 8, positive VCC. Pin 4, ground. If you are using single power supply. If you are using splitted power supply, positive VCC here, negative VEE here. Let's suppose if I use just only 20 volts, ground here, positive here. If I want to use 2 power supplies, I want to swing signal in positive side and negative side, then positive 10 volt here, negative 10 volt here. Ground will not be connected, common point will not be connected to this IC. Here is inverting input, non-inverting input. Inverting is pin 2, non-inverting pin 3. These are input signals. Pin 8, pin 4, ground. This time we will use only one power supply. This output, this input. Operational amplifier. Basically, it is a difference amplifier. It amplifies the voltage difference here. We want to compare 2 signals. One is 1 volt, second is 1.00001 volt whatsoever. So it will compare both signals. At this pin it is receiving 10 millivolt. At this pin 11 millivolt. 11 minus 10. It will amplify. It will amplify either the error is in positive side or negative side. So it will compare the input level on both pins, difference, then it will amplify. When we are using operational amplifier, it has open loop gain, AOL. Sometimes it is mentioned 200,000 volt per volt. That means if we provide 1 volt difference at input, one pin is at 0 volt, the second is at 1 volt. 1 volt difference will be multiplied with this number. It is called AON, open loop gain. That means 200,000 volt will be here. It will try to obtain this number, but it is impossible because we have limitation for the supply voltage. Maximum 20 volt, 15 volt, 32 volt. This is the limit. 100 volt per millivolt. If we provide 1 millivolt an input, we can program it to provide 100 volt. The same, here is 200,000 volt per volt as mentioned in datasheet for CA741E. And in this LA6358, if you provide 1 millivolt, it will multiply with this number. But we determine the input signal. What is input signal and what is DC rail? Now we will see it. First we will identify input signal. I have power supply 12 volt. I am using any transducer, any sensor that is providing some signal, some voltage. We will simulate that signal using a potentiometer. We will provide 12 volt here. Let's connect it. I have fixed volt power supply. 12.38 supply voltage. Because it is fixed voltage power supply, I am connecting one resistor, 102.4 kilo ohm. Nominal value is 100, but its practical value is 102.4 kilo ohm. And this potentiometer 10.04 kilo ohm. We will connect this potentiometer here with positive rail. Second end of this potentiometer will be grounded. This is R2, this is R1. V out, V supply into R2 divided by R1 plus R2. I have 12.38, 10.04 divided by 10.04 plus 102.4. Output here will maximum 1.1 volt. When resistor is at maximum position, we will receive 1.1 volt. Let's check this signal. When potentiometer is fully counterclockwise, we are receiving 0 volt. When we adjust this potentiometer, the voltage will increase. At full clockwise position, we have 1.105, same as we calculated. So we have 1.1 volt signal. Pin 8 is VCC, pin 7 out. This is second side. One operational amplifier here. Let me make it here. The second operational amplifier here. Pin 5 non-inverting input, pin 6 inverting. These positive signs indicating non-inverting input, and this one inverting input. IN inverting and I non-inverting. Now we have input 1.1 volt, output. Now how much output will in output of this operational amplifier? We have 12.38 volt power supply minus approximately 1 volt in the output from the output stage. Output approximately 11.38 volts. When input difference is maximum and we design gain maximum, saturated output will be 11.38. We will not reach up to this limit. We will reduce 10%. 11.38 maximum possible output minus 11.38 in 2.1. We will reduce 10%. We need output swing 10 volt. It is 10.42. We will consider 10 volt. What's that? This is 12.38 volt supply line. But this IC can provide 11.38. This is possible maximum high output, but we don't need to operate at this level. We will provide 10% headroom to the maximum output voltage, so we will operate this IC between 0 and 10 volts. This is in that case when we are using single supply to power up this IC. This is output. We have this supply line. We will keep spare this portion. We have possible output 11.38, but we will leave 10% headroom. Maybe the power supply is dropped, or maybe input signal level is increased than our 1.1 volt, or maybe the components are degraded with tolerance, with temperature. In that case, the output will go in saturation state due to power supply rail limits. Output waveform will be clipped off. Overdrive. We don't want to run this IC in overdrive, saturation or clipping mode. We have 1.1 volt. Here is input. Here is output. Input is swinging from 0 to 1.1 volt. Our input is swinging to this peak to peak voltage. 0 to upside. The same this signal, when it is rising from 0 with the same ratio which we will calculate, this signal will reach here. At input 0 to 1.1 volt, in output 0 to 10 volt with the same ratio. This is called gain. What is our required ratio? Output voltage divided by input voltage. Output voltage 10 volt. Input voltage 1.1 volt. 10 divided by 1.1, we need gain 9.09. This is our required gain. When we will provide 1.1 volt, the output will 10. If we provide 1 millivolt, 1 multiplied with this number, we will receive output. If we provide 0.5 volt, 0.5 multiply with 9.09, output will 4.5 volts. To set this gain, now we can drive this IC in different ways. The first, we will provide one reference signal and second error signal. In this session, we will use as non-inverting amplifier. This is output from pin number 1. Pin number 2 is inverting. Pin 2 inverting, pin 3 is non-inverting. Pin 8 positive VCC, pin 4 ground. We need to control the gain. For that purpose, we need a feedback resistor that is called negative feedback. We cannot adjust the gain until we use feedback resistor and input resistor. We take some portion of this output and we feed into operational amplifier input as a reference, and we provide signal here. This is from any sensor, any transducer. We need to determine the resistor RG, RF. If we are providing input signal at this pin, the output gain is 1 plus RF divided by RG. This is feedback resistor and this is input resistor. Now we have known gain 9.09. 1 plus RF feedback resistor. A good method, we must use high value resistor here, minimum 10 kilo ohm. I will use 10 kilo ohm. 9.09 minus 1 RF divided by 10,000, 80.9 kilo ohm. That means if we use this resistor 10 kilo ohm and this resistor 80.9 kilo ohm, the output gain will be 9.09. This is a calculated output. Let's verify it again using this formula. What will our expected gain? 9.09. Perfect. I will place this IC on the breadboard. The same method will be used to any operational amplifier. There are many other parameters like slew rate, common mode rejection ratio, power supply rejection ratio, output resistance, frequency, because it is a complete theory. I have this 10 kilo ohm resistor. Its practical value is 10.04. When we are discussing operational amplifier, practical value matters a lot. 10.04 kilo ohm. Feedback resistor This resistor will be connected between ground and pin number 2. Now we need 80 kilo ohm resistor. I don't have 80 kilo ohm. To make 80 kilo ohm, I will use 33 and 47 kilo ohm. 32.47 kilo ohm. This resistor 32.47 kilo ohm plus the second resistor 46.7 kilo ohm. We calculated 80.9 kilo ohm, but now the practical values, it is 79.21. We calculated 80.9, but it is slightly less than that value. If you want exactly the same number, then we will use a potentiometer in series with this resistor to adjust the gain exactly as we need. Or we can calculate now. 1 plus feedback resistor is 79.21 kilo ohm divided by 10.04 kilo ohm. The expected gain 8.889, slightly less than our calculated gain. We can compensate this value by adding a potentiometer to make it 80.9 kilo ohm. No problem. Now we will use these two resistors. 47 kilo ohm at pin number 1 and series resistor 33 kilo ohm, now one resistor. Now we will inject potentiometer signal to pin number 3. Now we will connect pin number 8 positive VCC, pin number 4 ground. Positive VCC to pin number 8, pin number 4 ground. This is our power rail. Now we will apply power. We will test signal now. Input signal at pin number 3. Input signal is varying from 0 to 1.1. And we will connect this multimeter at pin number 1 as an output. We have 1.1 volt. We have 1.1 volt input. We calculated gain 8.889, 9.779 volt, exactly 9.8 volt. That is perfectly matching to our calculation. If we provide 0.818 multiply with this number 8.889, that is gain 7.27. Exactly the calculated output is here. There is another parameter that is called input offset. That is a few millivolt input difference by default. When we are checking data sheet, we must take care for input offset voltage. That means if it is 1 millivolt, there will be output here because that difference due to its internal input circuit. Input offset is 7 millivolt. That means here 1 millivolt, 1 plus 7, 8 millivolt must here. That will be considered as a 0 because that is input offset error. That is by default. Some operational amplifier have null adjustment that will be used to compensate the input offset, but simple operational amplifiers don't use null adjustment. If we have 0 volt here, we need 7 millivolt here to make balance to the both inputs due to input offset error. That is not an error, that is by default manufacturing difference. As we calculated, the same calculated output is here in the output. If we have 100 millivolts, 0.898, perfect. Using same method, we can use the second side operational amplifier as well, because here I used pin 1 output. If we use second side, the same configuration will be used. We injected our signal here, 100K, 10 kilo ohm. We provide variable signal at this pin. So this is non-inverting amplifier configuration. We provide negative feedback to pin number 2 and we provide any signal here at non-inverting input. It will amplify that signal. The polarity of output signal is exactly as at input signal. That means when we are driving any operational amplifier as a non-inverting amplifier, output is in phase to the input. If input is increasing, the output is increasing with the same gain factor. If input is decreasing, the output is decreasing. In upcoming session, we will design inverting amplifier and we will see the difference. If you think this video is informative, give a thumb up. And what is your opinion about the video? Please write in the comments and share with your friends. Thanks for watching. Assalamu alaikum wa rahmatullahi wa barakatuh.